Okay, so hello for real, everybody, and welcome to the Exam 3 review. I'm sure you guys have seen the email by now, but Katrina and I will be hosting this together. We'll go back and forth, and we'll both explain different topics. And Katrina also sent the sign-in sheet into the group, into the chat. So please sign that, and when you do, just sign in under my name, Rosemary, so we can get all of the attendance into one place. As always, this will be recorded and it will be posted on the YouTube channel. It's going to be really long, so it might take longer than usual to post. I will set it up and try to post it tonight, but it could potentially be up tomorrow morning. So just keep that in mind. And yeah, the last thing I wanted to mention is this review will be 3 hours long, but feel free to leave or come back at any time because, again, it will be recorded. And attendance is not mandatory, obviously. Anything else you want to add, Katrina?
It's going to be run like last time, where while one of us is presenting and going over the topics, the other will be replying to comments in the chat. So if you guys do have questions and don't feel like interrupting, you could just drop it in the chat, and then we'll switch off on answering your guys' questions. That's it.
Cool. Okay. So yeah, I shared my screen, guys, so please let me know once you can see it so we can get started. And the last thing I want to say before I open it up to questions is this time we're going to try to go a little bit quicker, kind of. Like, we're still obviously going to cover all the concepts again, but instead of us just talking the whole time like we did last time, I'm going to ask for participation when we do the practice problems. So please don't be afraid to participate and answer either out loud or in the chat. And then people are saying they can see the screen, so awesome. And then someone asked, will Chapter 16 answers be posted because we didn't get to finish it? So that's a great question. I will be sending out like a cheat sheet to you guys, and please don't think it's like, I don't know, it's not an answer key or anything. It's just going to be like a 5-ish, 6-ish page review handout kind of thing that will have a summary of all the topics and all the chapters, and it will have everything kind of shortened, so you only have exactly what you need for the exam. So it's kind of like a Chapter 16 answer key, sort of, except it's only covering the most important topics, not every single detail that I'll do in SI. And anything that I didn't cover from Chapter 16 will be in the review today. So I hope that kind of answers your question. It was a long-winded answer, but it always is for me, isn't it? Okay, so let me switch over here. So if only it would zoom in like normal, that would be awesome. There we go. All right, so we are going to start with Chapter 16. Does anyone have any questions before I get started? All right, perfect. So Chapter 14 was all about aromaticity, and the first thing we're going to do is cover the basic rules for aromaticity. So in order for something to be aromatic, it has to follow all 4 of these rules, which are being cyclic, which means it has to be a ring, planar, which just means it has to be fully sp2, and fully conjugated. Oh, that is my bad. I wrote this under the wrong one. So being fully conjugated means that it has to be fully sp2. And all this means is we will have delocalization across the entire molecule or across the entire ring. So electrons can go all across the conjugated area. And the last rule is the 4n plus 2 pi electrons. And all that rule is saying is that in order for something to be considered aromatic, if it is cyclic, planar, and fully conjugated, you have to look at the number of pi electrons that are in the molecule. And if it is 2, 6, 10, 16, etc., that means it will be aromatic. We're going to skip non-aromatic for a second, and we're going to go to anti-aromatic, because anti-aromatic has the same exact first three rules. So it has to be cyclic, planar, and fully conjugated. The difference is that number 4 rule. So instead of 4n plus 2 pi electrons, we need 4n pi electrons. So what this means is if your system has a multiple of 4 pi electrons, that would mean you are anti-aromatic. So multiples of 4, 4, 8, 12, etc. So now that we have aromatic and anti-aromatic down, we are going to talk about non-aromatic. So for non-aromatic, the only rule is if it breaks any other rules, which is great because it's pretty broad, but it also kind of makes it easy for us to find patterns. So anytime you have sp3, you're going to be non-aromatic. Anytime you have an odd number of pi electrons, you're going to be non-aromatic. And here, this one I want to mention to you guys, if there is an odd number of radicals, so if you ever see 1 or 3 radicals, or more than that, but you won't ever see more than that, that means that you're automatically non-aromatic. If there's an even number, so if there are 2 radicals, you can't automatically say that it is non-aromatic. The last 2 things that I guess I didn't explicitly say in SI, but I want you guys to know, is that when we talk about a cyclic system, it does not have to be monocyclic. So it can be 2 rings, 3 rings, 4 rings, as long as it is cyclic somewhere in there, that is okay. So there probably will be a question that says, which of the following are rules of aromaticity? It does not have to be monocyclic. People always get that one wrong. That's why I'm saying it a couple times. Also, please...
Hey, Rose.
Yes, what's up?
Under aromatic, you put 16 instead of 14. That's all.
My bad. Thank you.
That's okay.
Like I always say, I can do orgo, I can't do simple math. Thank you, though. Okay, so... I forgot what I was saying. Oh, yeah, sp2. Please remember that radicals, cations, and anions count as sp2. Always, for this class. All right. So other rules are the ones that talk about heteroatoms and such. So please remember that heteroatoms, when they are single bonded inside the ring, can choose to either be sp2 or sp3. When we count it as sp2, it can only donate up to 1 pair of electrons. And if it's counted as sp3, we know that it automatically has to be non-aromatic. If you have multiple single bonded heteroatoms, they all have to have the same hybridization. So they all have to be sp2 or they all have to be sp3. If the heteroatom is double bonded, you no longer get a choice. You have to be sp2 hybridized, and you only donate 1 single electron. So the lone pair is no longer an option. It's only donating 1 electron in the double bond. If you have multiple heteroatoms in the ring, and only one of them is single bonded and the other one is double bonded, the double bonded one will have to be sp2, and the single bonded one can choose between sp2 and sp3. If the heteroatom is double bonded outside of the ring, such as a ketone, that carbon is going to count as sp2 hybridized, and it will contribute 0 pi electrons. So for that reason, we are going to just treat it as if it is a cation. And I'm going to repeat these rules one more time while we do examples, but I did want you guys to have a chance to just see them by themselves first. So these are a couple examples that go along with these heteroatom rules. So this first one has a nitrogen that is single bonded inside the ring. And we can see that this ring is cyclic and planar. So we're going to see whether the nitrogen will be sp2 or sp3. We already know that if it's sp3, it has to be non-aromatic. That's a given. If it's sp2, though, we have to count and see how many pi electrons we will have. So we have 2, 4, and then 5, 6 from the nitrogen. So we will have 6 pi electrons. And 6 pi electrons means that we follow the 4n plus 2 rule, which means that it is aromatic. So between sp2 and sp3, we know that the heteroatom will choose to be sp2, and so this ring will be aromatic. And again, just to reiterate, the reason we are choosing sp2 is because we will then have 4n plus 2 pi electrons, and we will be aromatic. And just to review stability things, aromatic is super, 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 super stable. Anti-aromatic is super, 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 super unstable. And non-aromatic is in the middle. So anytime we're between aromatic or non-aromatic, you definitely want aromatic. If you're between non-aromatic and anti-aromatic, you're always going to pick non-aromatic because you're always looking for the most stable option. And I'm trying not to look too much at the chat because I get a little bit distracted, but I did see that someone said they wanted me to go back to the rules. So just as a general little note to you guys, after I finish a section or a page, I will zoom out just so you guys can look at it again, ask any questions, and also screenshot if you missed anything. So I will be doing that. All right, so next on the list, we have another single bonded heteroatom, but now we have oxygen, and so it's a little tiny bit different. The only difference is, as you can see, I only drew one lone pair of electrons for oxygen, and we all know at this point that we have 2 lone pairs when oxygen is neutral, right? The reason I chose to not draw the other lone pair and only draw one is because the rule states if it is to be sp2, we can only donate up to 1 lone pair. So the other one is not going to count. So let's go ahead and do sp2 versus sp3. So we know that if it's sp3, we know that if it is sp3, it has to be non-aromatic because it breaks the conjugation rule. If it's sp2, we can go ahead and count the number of pi electrons. So we have 2, 4, 6, 7, 8. So 8 pi electrons. Now, we no longer follow the aromaticity rule. We have 4 pi electrons. So we know that it is anti-aromatic. So as I said before, when we're between anti-aromatic and non-aromatic, non-aromatic is always going to win because it is the more stable option. Therefore, this oxygen will be sp3 and it will not donate any electrons. So far we have done 2 examples of when we have a single bonded heteroatom in the ring. Now we're going to do an example when we have multiple single bonded heteroatoms in the ring. So, sorry, someone just asked in the chat, so it's non-aromatic? Exactly. This one will be non-aromatic, and the oxygen will be sp3 hybridized. Okay, so this next one, we have to remember the rule that, sorry, I looked at the chat again. Okay, so it looks like some people, either I misspoke or there was a little bit of confusion. So basically, if we are ever between anti-aromatic and non-aromatic, we are always going to pick non-aromatic because non-aromatic is more stable. Anti-aromatic super sucks. So if we can avoid it, we will not pick anti-aromatic. Kind of similarly, if aromatic is a choice, we're always going to pick aromatic because that is the most stable thing that something can be. Good? Okay, I think we are. So, back to this one. Remember, if we have multiple single bonded ones, they have to have the same hybridization. So let's do sp2 versus sp3 again. We know that if it's sp3, it automatically breaks the conjugation rule, so it has to be non-aromatic. And now, if it's sp2, both of them have to be sp2. So we count one lone pair from both oxygens. So we have 2, 4, 6, 8 pi electrons, because we have to count both. So 8 pi electrons would mean anti-aromatic. And now, again, we have to choose between anti and non-aromatic. And as we discussed, non-aromatic is going to be more stable. So that's the best answer. So we know that both of these oxygens will be sp3 hybridized. And neither of them will donate electrons. The last rule has to do with boron, and I forgot to read it before. I don't know why I skipped it. But boron is always sp2 hybridized, and it always donates 0 electrons. So we're always going to pretend boron is like a carbocation. So we don't get a choice. We can't pick between sp2 and sp3. It's always sp2. So we know this is cyclic, planar, and fully conjugated. Now we just have to count the number of pi electrons. So we have 2, 4, 6 pi electrons. 6 pi electrons means aromatic. So that would be our answer here. And someone asked, will they always have the same hybridization if there's multiple heteroatoms? Yes, if they are both single bonded. We're going to do this one in a second, and you'll see the difference. But for now, just know if they're single bonded, they will always have the same hybridization. Alrighty, so now we're going to do one where the heteroatom is double bonded inside the ring. So in this case, it has to be sp2. You don't have a choice. It has to be sp2. But it only donates 1 pi electron, and that is the electron inside the p orbital here that is making the double bond. So only 1 pi electron. So if we go ahead and count, 2, 4, 6 pi electrons total. We also know that we are cyclic, planar, and fully conjugated, so this ring will be aromatic. Again, we weren't allowed to choose between sp2 and sp3, and we only have 1 pi electron. So putting a couple of these concepts together, we are going to go here. So we have we have two heteroatoms. So we have to look and see whether they are single bonded or double bonded. In this case, we know only one of them is single bonded. The other one is double bonded. So this one has to be sp2. And we can decide between sp2 or sp3 for the oxygen. And we know that if the oxygen is sp3, it's always going to be non-aromatic. And if it is sp2, it will donate one pair of pi electrons, one pair. And so that would mean we have 2, 4, 6 pi electrons. We know that this follows the 4n plus 2 rule, so this will be aromatic. And let's just make sure this checks out. This is cyclic, planar, and fully conjugated when the oxygen is sp2, because nitrogen must be sp2 when it's double bonded. And we have a carbocation on this carbon. Everything else checks out, so we will have sp2 hybridized oxygen and an sp2 hybridized nitrogen, and we will have an aromatic ring. So I will zoom out to just these examples. And I will open it up to questions. And someone said, can I explain the last one? And I think by that you mean this one. So just to reiterate for this one, we have, let me zoom in. So nitrogen must be sp2 because it's double bonded. And the nitrogen itself only donates one single electron. So we can pretend that that nitrogen is just another double bonded carbon, because this double bond gives us 2 pi electrons, this double bond gives us 2 pi electrons, and this one gives us 2 pi electrons. So altogether we have 6, and so 6 pi electrons would mean aromatic. You are very welcome. Okay, and then someone said, in pyridine, the nitrogen atom donates 1 pi electron, but it's already in the double bond, so the total is still 6. That is correct. And I'm actually glad that you said the name of this, because we're going to talk about it later. But just so you guys know, this benzene-looking thing that has a nitrogen on it is called pyridine. And it's going to come back again later, so just know that's what that looks like. And then someone said, for cations and anions, they never donate anything, right? Sort of, kind of. So in the case of a carbocation, we have a plus charge and 0 pi electrons. In the case of a radical, we have no charge, but we donate 1 electron. And in the case of the carboanion, we know that it's a negative charge, and that means we have to donate 2 electrons. And then someone said, can I do an example with an anion? And some people wanted some other kinds of examples. So we're going to do a bunch more examples on aromaticity in the last hour. We picked out a whole bunch of examples. So I'm not going to do them right now, but I will do them at the end, just so we don't go back and forth too much. And then someone said, when we have a carbocation, does it automatically make the heteroatoms sp2? So no, the carbocation is only going to be this carbon, and it's just making that one carbon sp2. It's not changing anything else. So let me zoom out and move this out of your way so you guys can take a screenshot. Okay, so concept-wise, we are pretty much done with aromaticity. You guys had some really awesome questions. I'll give you guys about like 20 more seconds if you have any more questions. And then if not, I'm going to pass it over to Katrina, and she is going to do chapter 15 for you guys. And then someone said, can you repeat the question about cyclic that you said might be on the exam? Yes, I believe this is going to be in the practice problems again later. But if he asks you a question about like the rules of aromaticity, just know it has to be cyclic, planar, fully conjugated, 4n plus 2. Cyclic does not mean monocyclic. There can be multiple rings. It does not have to be monocyclic. And then someone said, will molecular orbital theory be on the exam? Actually, yes, it will, and I forgot to put it in here. So we can go over it in 1 second. Thank you for bringing that up. I forgot. And then someone asked about naming different kinds of aromatic rings. We are going to do that like at the end of chapter 3 after Katrina's done. I have them all drawn out, so we're going to go ahead and name those at the end. Okay, so I'm going to stop sharing for a second, and I'm going to open up the MO theory stuff. Okay. I have so many things. I'm sorry, guys. Okay. So please let me know once you are able to see my screen again, because I'm sharing it. Can you guys see the screen? Please let me know. Yes? Okay, cool. So the first thing we are going to do is benzene, and we're only really going to do 2 molecules because that's all that ever really pops up on the exam. So benzene itself will have 3 double bonds, which means we have 6 carbons that are going to have p orbitals. So I will draw that out super quick. Like this. And each of these are going to have 1 electron in them because of the double bonds. And so now we can see that 6 p orbitals means that we are going to translate that to 6 molecular orbitals. So I will write that up here, 6 MOs. And we also know that we have 6 pi electrons. So I'll also write that down. So I've already drawn kind of how this is oriented, and I wrote some things in just for the sake of time. But something that's different from chapter 13 that comes into aromaticity is that now instead of having 1 orbital per energy level, we're going to orient this to match the orientation of benzene. And what I mean by that is when we draw the molecular orbital diagram, we're going to put a line, which corresponds to an orbital, at each point in benzene, like this. Don't ask me how they came up with this because I have no idea. That's just how we do it. And so we have to introduce a new concept when we talk about this, since now we have multiple orbitals per energy level. and we call that degenerate orbitals. So degenerate orbitals are just multiple orbitals that are on the same energy level. And I'll repeat that because it's a mouthful. So degenerate orbitals are just more than one orbital on the same energy level. And so as I'm pointing here, we have two pairs of degenerate orbitals because these two are on the same energy level and these two are on the same energy level. One last thing I want to bring up that's different from chapter 13 is how we split up bonding and antibonding. So now in aromaticity, I don't want you guys to think of it as exactly the same as chapter 13. So back in chapter 13, we said anytime you have an even number of anytime you have an even number of orbitals, we said that there was going to be no non-bonding, and we were just going to split it in the middle and have half bonding, half anti-bonding. Sort of kind of still true, but now instead of thinking about in terms of actual orbitals, we're going to think about energy levels. And I'll explain again what I mean by that. But when we have degenerate orbitals, both of them have to be the same. So antibonding and bonding, if it's on the same energy level, it has to have the same title, I guess you can call it. So both of these have to be bonding. Both of these have to be antibonding. So now when we draw it, we're going to put a line in the middle here. And anything under the line is going to be bonding orbitals, excuse me. Anything above the line will be antibonding orbitals. And if I had something on the line, that would be our non-bonding. You'll see more of what I mean in the next example. But in the case of our benzene ring, there are 1, 2, 3, 4 energy levels. We cut it in half. The first two will be bonding, and the second two will be antibonding. That was really long-winded, and I know it was a lot. It was a mouthful. Let me know if you want me to repeat anything. I just wanted you guys to have this down, the differences between chapter 13 and 14 when it comes to molecular orbital forming. While you guys write down any questions you might have, let's go through and fill up our orbitals with electrons. Another tiny difference is when we're filling... What was that?
I'm sorry. How long will it take before this is posted?
So this will be posted either tonight or tomorrow morning. I have no idea how long it'll take to upload on YouTube, but I'll upload it tonight.
Really? Okay.
Okay. Someone said I can't hear you. Can you guys hear me now? Is there any problem? Yes? Okay, so we're good. All right. Anywho's, I kind of got lost with what I was saying, but filling in orbitals. That's what I remember last saying. So, sorry if I repeat myself, but the difference between chapter 13 and chapter 14 when we talk about filling in orbitals is we have to do them one at a time. So what I mean by that is on the first energy level, we only have one orbital. So we fill that one up. We go up to the next energy level, and we're not going to fill up pi 2 and then move on to pi 3. We're going to do 1, 1, and then go back and fill it. Sorry about that. Go back to pi 2 and finish it up, and then finish up pi 3. Not a big deal in the case of benzene, but it will be important in the next example, so just keep that in mind. Alrighty. So in the excited state, the only difference is going to be that we are going to take one of these electrons from pi 3 and move it up to pi 4. So keep those the same. And now we have one electron in pi 4. So we know that the HOMO is the highest occupied molecular orbital, and that will be pi 3. And the LUMO is the lowest unoccupied molecular orbital, and that will be pi 4. So this is it for the drawing of the diagram. Now, real quick, I will tell you guys the numbers verbally. So, in the ground state of benzene, we have 6 bonding electrons and 0 non-bonding electrons. We have 2 electrons in the HOMO, 0 in the LUMO, and we have 3 bonding orbitals and 3 anti-bonding orbitals. We also know that we have 2 pairs of degenerate orbitals. In the excited state, we moved 1 electron from the HOMO to the LUMO. So now we have 5 bonding electrons and 1 anti-bonding electron. We have 1 electron in the HOMO and 1 electron in the LUMO. Everything else stays exactly the same. So I'm pretty sure this is zoomed out enough that you guys can see the whole thing. So let me know if you have any questions, and I'll give you guys 30 seconds to screenshot or do whatever. So yes, someone asked about the degenerate orbitals. We still have 2 pairs of degenerate, but when we talk about single orbitals, we have 4 single degenerate orbitals. We have 2 pairs of degenerate orbitals. Okay, so if we have no other questions, let me go on to cyclobutadiene. We're going to zoom up. Okay. In the case of cyclobutadiene, I'll give you guys a second because I know I already have a lot of stuff written on the screen for the sake of time. But essentially, we're going to do the same thing as we did for benzene. So we're going to tilt the square to look more like a diamond. And we are going to put a line at each point of the ring. And so each of these lines corresponds to a molecular orbital. Now we have 3 energy levels. So when we cut it in half, unlike in benzene, we don't have an even number, and we have something on the line. So when we cut it in half, as we said before, whatever is under the line will be bonding. Whatever is above the line will be anti-bonding. And what we have on the line, we are going to call non-bonding. So let me erase the obnoxious line. So for cyclobutadiene, we have 1 bonding electron, we have 1 bonding orbital, we have 1 anti-bonding orbital, and we have 2 non-bonding orbitals. Please note that the 2 non-bonding orbitals are also degenerate because they are on the same energy level. So now we have 4 pi electrons, and when we go about filling that up, we fill up the first layer, and then we go up to the second one, and we do 1. I'm so sorry, I don't know why that keeps happening. 1 in pi 2, and 1 in pi 3. And now we ran out of electrons. So the reason that antibonding is so unstable is this right here. So as we can see, we have 2 half-filled orbitals, and that is super, 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 super unstable, and that is why anti-aromatic rings are super unstable. They will all have this half-filled energy level. In the excited state, that last electron from pi 3 goes up to pi 4. And so now we have something weird. In the excited state, we'll have 0 electrons in the HOMO and 1 in the LUMO. In the ground state, we have 1 in the HOMO and 0 in the LUMO. So it kind of does a flip-flop when it gets excited. So let's verbally go through the numbers one more time. So in the ground state of cyclobutadiene, we have 1 bonding orbital, 2 non-bonding orbitals, and 1 antibonding orbital. We have 2 bonding electrons, 0 antibonding electrons, and 2 non-bonding electrons. We have 1 electron in the HOMO and 0 in the LUMO. In the excited state, we have 2 bonding electrons, 1 non-bonding electron, and 1 antibonding electron. And for both of them... Oh, sorry, go ahead.
What did you say about... Can you say the rule about the line again?
Yes, I can. So basically, all I was trying to say with the line is when we're trying to decide whether or not there's non-bonding electrons, you just take this diagram and you cut it in half like this, right? So when we cut it in half, we know whatever is under the line is bonding, whatever is above the line is antibonding, and whatever is on the line in the middle, that is going to be non-bonding. So that's how we assign non-bonding when we have aromatic rings.
All right, thanks.
You're very welcome. Okay, so let me just zoom out a little bit. And I'll give you guys a couple seconds to screenshot, and then this time for real, we'll pass it over to Katrina. And yes, someone asked me to go back to benzene. Yes, I can do that. Just I'll give it a couple more seconds for this one. Okay, I'm going to scroll away. Last chance. Okay, now I'm leaving. And here we are for benzene. And then someone asked, would he ask questions from MO from chapter 13 on this exam? No, he'll ask you this stuff on the exam. Okay, so I am going to stop sharing now. Why won't it let me do that? Stop. Okay. And then someone asked, what about bigger molecules for aromaticity? No, don't worry about it. Just focus on the simpler ones because in my experience, Dr. West doesn't ask for bigger molecules. He sticks to benzene and cyclobutadiene.
Okay, I guess I'm taking over now. I think she was referring to the annulenes, and when it comes to the annulenes, guys, you just really need to count the electrons. That's what it really is for aromaticity. So yeah. Know the annulenes. He usually only puts like one of those on the exam anyways, just to scare you. And that's about it. And thank you, Jared. I appreciate it.
Also,
go do your Order 3 project.
Sorry, I just want to add on to what Katrina said. We're going to do some examples of annulenes, but that'll be at the end, like I said.
Yeah. So don't stress too much about it, guys. We will cover it. If we think it's going to show up on the exam, we'll cover it. Okay, guys, so chapter 15, our long-winded chapter about directing effects and a bunch of different reaction mechanisms. Important thing to note before I start, remember that these are all going to... I don't know what I was trying to say there. Never mind. Ignore me. I'm a little out of it. Okay. So let's go ahead and get started, guys. So we're just going to start out with a basic mechanism of this. So remember that these are done via substitution, not addition. Very important to note, it will only undergo substitution, not addition, because we do not want to break the benzene stability. So remember, we will always end up with a stable molecule at the end. Okay, so we're just going to run through the reaction mechanism really, really quick. So what really happens is that the reagents will react with each other first. Yes, these are, I can't say the whole thing out, but yes, EAS. So what's really going to happen is that our two reagents are going to react with each other first. So this Br is going to attack the iron, the FeBr3. So we will end up with our thingy looking like this, Br, FeBr3. So our Br here will have a positive charge, and this guy over here will have a negative charge. And then what happens is that, let's say, I'm going to draw on a double bond here. This double bond here is going to attack this Br, popping it off from the rest of the group. This step, since we are losing the aromaticity of the benzene, this is going to be our rate determining step. So remember, whenever you break the benzene stability, that is going to be your rate determining step, because benzene likes to be stable, so to make it unstable, it's going to take a while. Okay, so we now have a Br here. Sorry guys, my handwriting sucks. There's a hydrogen, and there's also a hydrogen down here, and this now has a plus charge because the double bond is gone. We still have the leftover Br, Fe, Br3. Our iron is negative, our Br is still positive, so what's going to happen is that this Br here is going to take this hydrogen, and then the hydrogen's electrons from this bond are going to get donated in to reform our double bond. So in this step, we are regaining aromaticity. So we will end up with just a Br here. And if you guys want to see the byproducts for this, I don't know why I did that in that color, but I did, is HBr and then FeBr3. Those are our byproducts. Another important thing to note, in case he asks this on the exam, this is called the rhenium ion, and it's when benzene has this positive charge. This is its ion state. So rhenium ion, just in case he asks. Okay, so that is the basic mechanism for literally every single one of these that we are about to go through. So follow the same steps and you'll basically end up with the same thing. You don't really need to know the mechanism, as always. Basically just know if we have this reagent, we're going to be forming this product. So let's go ahead and hop into it. Let's start out. I'm going to start with nitration, and then we're going to work our way this way. We'll save Fritocrafts for last. So in nitration, our reagents are HNO3, and it's going to be over H2SO4. Because remember, we do need to have a catalyst for this reaction. So in this case, this is our catalyst, which is also just called a Lewis acid. Okay, so let me move this guy up here. Our electrophile for this reaction is the nitronium ion, and it looks like this. So all this guy does is that we tack on, this is not going to fit over here, so I'm just going to put it over here. It doesn't really matter where you put it. Yeah, it's not going to fit over there. I tried. we're going to put it over here. So there we go. You just pop on the NO2 onto the ring. And yeah, that's how we do our nitration. Sulfonation looks like this. So in sulfonation, the only difference between nitration and sulfonation is like the top reagent. So in sulfonation, SO3 is our top reagent, and then the bottom one is still H2SO4. So once again, this is our catalyst for this reaction. And the electrophile for this is going to be this guy right here. Positive charge on our oxygen. And there we go. All right, so we do the same thing. We just pop on the group. I'm going to put it over here. And remember, we add on SO3H, not just SO3. So yeah, okay. And then halogenation. Halogenation is like the example that we did for the reaction mechanism. It is some halogen, which is represented by X, over Fe, some halogen to the third. Okay. So those are our reagents. Our electrophile for this guy, which we already saw, looks like this. So then we're just going to add it on to the benzene ring. We're just adding on the halogen. Okay, so now we get to the Fritocrafts, which always confuses people, which is no big deal, because when I took this class, it confused the crap out of me too. So an important thing to note before we get started on these reactions is remember that Fritocrafts will not, that says mot, will not occur in the presence of a strong deactivator or a NH2 on the ring. This is something you just need to know about rules. So please, please, please know that the Fritocrafts reactions, whether it's acylation or alkylation, it will not occur in the presence of a strong deactivator or NH2 on the ring. NH2, not NH3. Okay, so in alkylation, let's see which color I didn't use yet. Let's use this one. In alkylation, we will have an alkyl group, of course, over AlCl3. Our electrophile in this reaction will be a carbocation. And something important to note about this one is that it can undergo rearrangements and it can undergo polysubstitution. And all that means is that we could keep on adding on the alkyl group. We could keep on adding on the R group until we fully substitute it. If we have enough of it, if we have it in excess. So I really don't want to get into the whole why NH2 wouldn't work for the Fritocrafts because it's a really long story. Yeah, there we go. Rosemary got it in summary. It's basically a strong activator and it's the strongest one, so it will act like a base, like a strong base, which I know is confusing, but don't worry about it. Just know it won't occur if that's present. Okay. And last but not least, we have the acylation, which is RCOX, where X is literally any halogen once again, and R is our alkyl group, and it will be over AlCl3 once again. Our electrophile, this guy's a little funky. So we have two forms of it. So positive. So these guys are both called the acylium ion. Just know that one is the reactive form while the other one is the stable form. So we use this one in our reaction, but this is just its stable form. So, oh, sorry guys, I forgot to draw in. Why did I do that? I forgot to draw this in. R group for alkylation. My bad. So for this guy over here, all we are going to do is bond on the acetyl group. I always mispronounce this, so I had to say it really carefully. But we bond on the acetyl group. We do not bond on the halogen or anything. It is just this as our end product. Okay, so that is it for this page. So go ahead and take a screenshot of this if you want. But yeah. For the Fritocrafts reactions, yes, the catalyst will always be AlCl3. So that's an easy telltale sign if you're doing a Fritocrafts reaction. If you see AlCl3, you will likely be doing a Fritocrafts reaction. So yes. Yes, we can do poly substitution if we have more than like 1 mole of it, and then we could do a poly substitution. But if we do excess, then yeah, we would definitely be able to do a poly substitution. Will it ever be any other halogen? For which one are you talking about? Are we talking about? No, it's usually just AlCl3. We won't really use any other halogen. It's just AlCl3. Okay, so hopefully everybody got a screenshot of this. I do not want to spend too much time on this, so we can get into practice problems. So I'm going to go ahead onto the next page. So now we are going over directing effects. Directing effects are always fun. Basically, we're just going to show you how things resonate when we do these. So let me pull up my stylus again. All right. So this oxygen here has lone pairs, and what it's going to do, donate in, push this guy out. Thank you, Jared. I need to stop looking at the chat. I know you guys got it. I don't know why I keep looking at it. It's like, it's very tempting to read the questions. Okay. And then these guys stay here. We're going to keep going. Oh, wait, did I specify which one I'm doing? Sorry, guys. Let me specify. This is for ortho, para. Sorry, people are calling me. These are ortho para activators. And this is just how we resonate it. So then we just keep going, keep pushing it around the ring, pop this guy out over here. Now we have a lone pair of electrons here. Sorry, I don't know why my circles look so bad today. And then we'll end up with this, push again, pop that guy out. Negative charge, double bond, and one more time, we will push this guy in here, and we will put that up there. So now, once again, our oxygen has that, and all of these guys will have a partial negative to them. Okay. So then for our ortho-para deactivators, which are basically halogens, I will leave the ortho-para activators up while I go into the next one. This is simply just resonance, so it shouldn't be too crazy. Just find the lone pair and just push it in. So remember, the activator versus the deactivator. We only have a couple of deactivators, and they're always the ones that are going to be halogens bonded to the benzene. The orthopara activators, it's this sheet, guys. The summary table of aromatic things. So yeah, that's all we're doing. We're just showing the resonating effects. So for the BR, here are all of our electrons. We are going to do the same thing. We're going to start pushing electrons around. So form that double bond, kick this double bond out. So we will now have a love pair here. Push this guy in, push these electrons out. A lone pair here. And keep going. Push this guy in, push this guy out. And then finally, for the last one, push this guy in and push that double bond up. So now our BR once again has its full electrons, and these guys will once again have a partial negative pull. He honestly won't really, okay, I'm not going to say that. If he asks this in a question, it's going to be like the practice problems that he already gave you. It's basically just going to say which one of these is a major contributor to the resonance stability of this molecule. So he's just going to give you a bunch of different ones, and then you just have to identify which one is going to be the most stable. That's it. Okay, and then finally, last but not least, is our meta deactivator. So if we're talking about which one's going to be more stable, notice how this one is the same. It's just moving the double bonds around. The way he would give you a question is that he'd give you like these four here and be like, which one of these is the most stable out of the four of them? He's not going to give you this one and this one because they're basically the same thing. So just be able to identify between like these four.
Wait, so is the first one more stable? Like the first,
So guys, just remember this guy here has the same conjugation as this one here. Notice how the BR has all of its electrons, and then we have a fully conjugated benzene. So we're looking at between these four here, or it could be these four here. I'm just saying that there's no difference between this one and this one. So it wouldn't make sense that he would give that to you as a question. It would be between these four. So this is the most stable. Okay. Hopefully that clarified some things. Exactly. Like Rosemary said, the most stable will be the one with the least number of charges on it. We don't want a lot of charges on our ring or just on the molecule in general. So whichever one has the least amount of charges will be our most stable molecule. Okay. So now this guy here, meta deactivators work a little differently. They're going to go this way and then push up there. So we're first going to end up with our oxygen losing its double bond. And then we will have these bonds still here. And there will be a positive charge here because notice how that double bond's gone now? The double bond will leave a positive charge here. And then what's going to happen is that we are going to resonate with this. So we are going to push this double bond over here, which is simply just going to move the positive charge elsewhere. The positive charge goes where that double bond used to be. So we end up with this. Notice how this guy and this one just kind of switch places. Okay. Then another way we could do this is by pushing this bond here. And that will simply put a double bond here and one here, and the positive charge goes over here. So double bond gets switched with a plus charge. And then finally, after we push this guy, we will push this double bond downwards we are going to get rid of this plus charge because now there will be a double bond here, as you can see here. So all of these guys are going to be partially positive. Okay, so if you guys do want to know which one's the most stable, the first one and the last one are the same exact molecule, so they are going to be the most stable. And the O electrons, yes. So these guys move down here to reform our double bond here. Okay, so I still have the rest of this page to go, but I will let you guys take a screenshot of the top half for a second. Okay, I'm going to start scrolling. So now we're doing the order of reactivity. Now we're specifically talking about our orthopara activators. We're breaking up the groups. So if you look down here, guys, we added this nice little chart for you guys, which is basically this guy, but drawn out in a straight line and not with it all staggered. So this is basically what you guys need to know. Know that these are your orthopara activators, and they are going to be most reactive going this way. And then these are your only orthopara deactivators. And then all of these are your meta deactivators. And these going to the right will be the least stable. Well, not least stable, least reactive, my bad. So this is in order of reactivity. So if you guys want me to draw a line, that was such an awful looking line. Reactivity. Okay, so for the orthopara activators, if we were to write all of them out in order of reactivity, I really don't want to. Okay, so we have the, I'm not going to draw out the benzene. I'm just going to draw out the groups that we're dealing with. So NH2 is going to be our most reactive, and then after that, we will have our OH. After the OH, we will have a oxygen with an alkyl group. After that, we will have nitrogen. This NH bonded to the benzene. And then we will have, this is the one that trips everybody up, so don't let this one trip you up. This here is a activator. And the reason why it's an activator is because this oxygen here is the one that's attached to the benzene. You'll see later when I draw out the deactivators, the difference between this guy and then this guy here. So when I get there, I will show you guys that. And then finally, we can have an R group, which is just like an alkyl group. All right, so the only orthopara deactivator we have are the halogens. So X is literally any of the halogens, which are Br, Cl, iodine, and I don't know if I'm missing more. I might be, but those are the main ones. Okay, and then meta deactivators. So we are going from the most reactive to the least reactive out of our meta deactivators, so out of these guys here. So out of all of these guys, the most reactive one, which we don't really have drawn on here, is a aldehyde. And then we will have I don't really like the way I'm drawing this right now. OCH3. And then after that, we will have our carboxylic acid, And then after the carboxylic acid, we have the ketone. After the ketone will come our SO3H, then our C with a triple bonded nitrogen, then NO2, and finally NR3. Our alkyl just means like any alkyl chain. So that just means like any of these guys are just alkyl. So they're just carbons and carbons and hydrogens. So guys, please just know these in this order. Remember, I'm doing most reactive to least reactive. So in case he does ask you about that, I don't think he will necessarily specifically do that. But yeah, this is them in order. But Rosemary gave us this nice little sheet on the bottom. So I'm going to go ahead and zoom out of this entire page so then you guys can grab a screenshot of this. Yeah, that's really just like an ester. It could be any alkyl group. I only put OCH3 because that's what I had on the chart, but it's any alkyl group. So let me change that really quick. So then it's a little bit more broad. Okay. Yeah, ketone, the same thing. I just drew it as 2 CH3s just because it was easier. But you could literally have any alkyl group. But the important thing to remember, guys, remember how I said this guy is going to be different than one of these guys here? Notice how the oxygen is the one bonded to the benzene ring? Like over here, the oxygen is bonded to the benzene. Versus in the other situation, the carbonyl with the double bonded oxygen is directly bonded to the benzene ring. This one always gets everybody tripped up, but just remember the difference between the two of them. Okay. So we do have directing of practice, but before I go on, does anybody have any questions? I know Rosemary has been doing an amazing job answering the questions in the chat. All right, I'm going to take that as a no.
I have a quick question.
So I'm going to keep going. Oh, somebody has a question?
So anytime that we see a group with lone pairs, we can think that it's an activator because it has the electrons to facilitate the reaction. Just so I keep it straight in my head.
Yeah, basically, for most of the cases, you can see that because the nitrogen here, all of these guys all have lone pairs. Just don't get tripped up on like these two over here in the meta deactivators.
Right.
So
okay.
If you want to memorize it that way, by all means, go for it. Just make sure that you realize that these guys, these special ones right here, are going to be a little different.
Okay, cool.
Yeah.
Sounds good to me.
And guys, I promise when we put it all together in the end, when we go through practice problems, it's going to make a lot more sense. And yes, halogens are the only deactivators with lone pairs, and that's why they are considered, these guys are weak deactivators. So yeah. But NR3 just means a nitrogen with 3 R groups, so basically a tertiary amine. So this can be any alkyl group. Just like how this is our alkyl group, it's just a bunch of alkyl groups bonded to the nitrogen. Okay. So let's go ahead and go into some practice problems so then we can really get this stuff down. Okay. So let's go ahead and do some of this. So we have this CH3 group. What is this CH3 group going to be? What type of, is it going to be an activator or a deactivator? Yes, perfect. It's going to be an orthopara activator. So this guy here is a OP activator. So we know that it's going to direct ortho-para, so we can bond it here, here, or here. Because remember, our ortho is 1, 2, and our para is 1, 4. So we can end up with the BR being here. But we can also have the BR appearing down here in the para position. I am an absolute mess right now. Let me see. Okay. So just notice, guys, we can bond it here or we could bond it here. The reason why I didn't draw one over here is because we can flip it over like a pancake and you'd end up with the same molecule. All right, so let's look at our next one. This Cl group here, what is this? Activator or deactivator? And what is it directing? Okay. Yes, it is a ortho-para. This guy here is an ortho-para ortho-para deactivator, I'm sorry. This is a halogen, guys, so remember, if it's a halogen, it's a weak deactivator, so we can still... So what reaction are we doing here with this? Yes, we are doing Fritocraft. Galen, in regards to that chapter 15 practice problem, they can be two separate answers unless he states that we're going to be doing it in excess, so we would bond again, but I don't... He does do that where he just kind of draws them onto the same molecule. If that was the right answer, for that, he simply was just trying to show you that you could bond it ortho or para. It's weird, but yeah. But yes, this is a Fritocraft alkylation. Yes. Thank you, Rosemary. I'm gonna get distracted. I need to stop looking at the chat. All right. So yes, this is a alkylation, and it's a Fritocraft. I'm just going to put FC. So remember, this guy can undergo rearrangement. So when we turn this guy into a carbocation, we can do a rearrangement. So then we end up bonding on the molecule looking like so, where we have one here, Cl, and we can also have one here, Cl. And I did not draw our directing effects, but orthopara. And to answer your question, Abigail, this one can happen because it is a weak deactivator. If it was a strong deactivator, which is our meta-directing ones, we can do the reaction still.
Wait, did you do rearrangement for the CL right there? Or is that how it's supposed to look? 'Cause
it is, just because, okay, this is a little, how do I draw this out? So it basically looks like this.
How you connect it with the middle, or I don't know.
Where did you move it?
Hold on.
To like the right?
If we moved it to the right over here.
No, I'm talking about like
something wrong.
connected in the middle.
Okay, sorry.
Or,
I was trying to type it in the chat, but it was taking too long to type. So basically, I understand what you mean by the rearrangements, but in this case, we can't do a rearrangement because we only have an ethyl. So we only have 2 carbons. No matter what we did, it would still end up primary. But you're right. If we had a longer chain or any kind of bigger chain where we could do a rearrangement, we would. But in this case, it wouldn't make a difference because we'd get primary either way. Make sense?
Yes, thanks.
Okay, you're welcome.
Okay. Yeah, that was kind of a bad one to mention rearrangement for, because, like she said, you could end up, it would literally be the same thing if you put it here or here. But this is what it looks like when it bonds on, because you kind of think of it this way. This is where the positive charge was, and then we created that bond between the carbon and this carbon here from here. Okay. Sorry for the confusion, guys. All right, so we have an NO2. I'm going to kind of go through these a little bit faster now. NO2 is going to be a meta-directing deactivator. This is a strong deactivator, but we're not doing Fritocrafts, so we don't really care that much. We are dealing with SO3 and then H2SO4, which means we are doing a sulfonation. So we know this is meta-directing. So we are going to draw in our arrows. We could bond here or here. I always hate how my benzenes look, but it's fine. It's fine. NO2, and then I will pop on the SO3H here. The only reason I'm not going to spend time drawing it on the other side is because, once again, if we flipped it over like a pancake, we would end up with the same product. Yeah, thank you, Rose, for that. Okay, so here we go. We don't really see this too much, but here's our triple bonded nitrogen at the end. So this guy here is, once again, a meta deactivator. I am still laughing. I need to stop. So we are going to bond it either here or here. And we are doing a Cl2 FeBr3, meaning this is a halogenation. So let's go ahead and draw our benzene. Of course, I'm like the one who has to draw all these benzenes. I should be like a pro at this by now, but I'm not. It's really sad. It's a sad day for me. All right, so Cl over here, or we could have had the Cl over here. Once again, flip it over, you end up with the same one. So, because in these guys, we do have symmetry in the middle. Okay. I will let you guys screenshot this at the end, so please do not worry if you guys aren't writing these down as fast. Yes, Notability does need to have a benzene stamp. Somebody make it. I will use it all the time. And yeah, the circle in the middle benzene is so much easier to use. Okay, so I am going to ask you guys this one. What is this guy here? Is it going to be an activator or a deactivator? Yes, you guys did not get tripped up like I always do. This guy here is an activator and is going to be a orthopara activator. Perfect. So we direct here, here, or here. So we will have boop, boop. We can add on our NO2 here. Or we can add on our NO2 over here. All right. So finally, let's go on to this guy here. What is this guy here? Activator, deactivator, perfect. This is a deactivator, and it is a meta. What reaction are we doing? Perfect, everybody got it. It's a Fritocrafts FC, and it is a acetyl one, and it will have no reaction, and that is because we have a strong deactivating group, So our poor Fritocrafts cannot do its reaction. Yes, as just says, you guys are extremely smart. You guys are pros at this already. Full faith. Okay, now we get a little trickier. We are going to do multiple substitutions. This is always the fun part. So I always do mine in 2 different colors, so bear with me if it, oh wait, let me let you guys take a screenshot of this first, sorry. I completely forgot about that. Go ahead and take a screenshot, guys. Let me get, okay, perfect. But basically, if a rainbow looks like it puked on my page, don't worry about it. That's how literally all my SI notes look, and I'm sorry, honestly. Okay. So I'm going to scroll onwards, and we will start doing multiple substitutions. Once again, I know, see, I'm one of those people that needs colors, so that's honestly how I get my grades. All right, so OH is a ortho-para activator, and then this guy here, our NO2, is a meta deactivator. So let's go ahead and draw in our arrows. Ortho-para can bond here, here, or here, and then NO2 is going to want to bond meta, which is here or here. None of our arrows line up, and since none of our arrows line up, that means we must follow the strongest activator. So if we're following our strongest activator, which in this case is the OH, benzenes take forever to draw, we will bond our NO2 here, or we can bond our NO2 over here. So notice how I didn't say this guy here would be a product. Technically speaking, it can be a product, but we don't consider it one because it will rarely happen since steric hindrance. So this guy here will not happen because of sterics. So these are your 2 possible answer choices for them. Remember, when none of our arrows line up, we go based on our activator, or our most activating group we have. Okay. So now we have this guy here. This is a ortho-para activator. This CL here, I need 2 different colors, is a ortho-para deactivator. Sorry, I'll slow down a little bit. I just don't want to spend too much time on it. Okay. So let me draw in our arrows for this guy here. So we're doing ortho-para. So these are the places where they would bond. And then the other guy is also ortho-para. So we would bond here, here, or here. So all of their arrows line up, but remember, this guy here will likely not form, and the reason for it, once again, is because of sterics. So since we have sterics, we won't say this guy is a product, so we can end up with bonding the Cl here, or we can bond our Cl here. So that is how we do that for this multiple substitution. In this case, it worked well because our arrows did kind of point to the same places. So those are our 2 possible answers because this third one here does not work from sterics. Okay. So I'm going to move on to the next one. I will keep these 2 problems still up on the page. Here, once again, this is simply an alkyl group, and since it's simply an alkyl group, it is an orthopara activator. Our Br here, once again, just like the Cl, is an orthopara deactivator. Remember, all of our halogens are orthopara deactivators. So I'm going to go ahead and draw in our alkyl groups directing effects, which would be here, here, or here. And then our Br, we're going to do the same thing. It directs here, here, or here. Once again, our arrows do not line up whatsoever. So we have to go based on our strongest activator on the ring, which in this case is going to be our alkyl group. We are doing a Fritocrafts acylation. Notice the AlCl3, and then this guy has this double bonded oxygen. That is how I tell that we are doing a Fritocrafts acylation, not an alkylation. This guy cannot undergo rearrangement, and we do not have a strong deactivator, aka a meta deactivator, so we can carry on with the reaction. So since we have to direct based on our strongest activator, we will bond here. Oh my god, I didn't even realize what I had to draw out. Okay. Boop. We can bond here. Let me move this up there. Or we can bond down here. So remember, we chose to go based on our strongest activator because none of our arrows lined up. Then this is a Fritocrafts acylation, and since we do not have a strong deactivator present, we are able to carry on with the reaction. Okay. Yes, we are choosing even if we have two activators and they do not line up, we will still choose the stronger activator to go based on. Okay, so here we are. This guy is going to be a meta deactivator. Our NO2 is also a meta deactivator. So I'm going to go ahead and draw in their arrows. 1, 2, 3. And then our one for our NO2 will direct here or here. So this is one of those situations where we need to choose between the two of these two and see which one is more reactive than the other. So technically like the less strong deactivator. So if you look at your chart or the one that Rosemary gave us over here, this isn't going to work too well. Basically, look at your chart. You will see that our C triple bonded N is going to be more reactive than our NO2. I know you guys probably can't see it, but the NO2 is all the way down here, and the C triple bond N is slightly before that. And since this guy is more reactive based on our scale, we are going to use the C triple bonded N as our director. So because of that, NO2, triple bonded nitrogen, we will bond the SO2 either over here or over here. Am I adding on the wrong group? I think, yes, it's SO3H, my bad. Let me erase this guy here. Yes, it's SO3H. The rule for where it bonds, if you're talking about like which one we choose over the other, it's going to be based on which one is more reactive. So that is why we went over the reactivity of all of our meta directors, all of our ortho para directors as well. So in this case scenario, this guy here is going to be more reactive than our NO2 if you look at the chart. And that is why we use this guy to direct where we bond on the group.
I'm sorry, I couldn't type fast enough. I was trying to figure out because for method deactivate, it's 2 away from where the I don't know what to call that, where the method deactivator is. So it's 2 from there.
Yeah, so metas direct 1, 3. So this is 1, 3, and then this is also 1, 3. And then if we go based on this guy here, we are bonding 1, 3, and 1, 3. Does that help?
Yes. What about for the OP activator and OP deactivator?
So let me draw that up here really quick. So ortho will bond 1, 2. Para will bond 1, 4. And then meta will bond 1, 3. So those are our order. All right. I think we're good. All right. So we only have 2 more problems, guys. Like, OMG, that's how I remember it. That's a good way to remember it. All right, let me continue on. So our OH here is an ortho para activator. And then this guy here, remember guys, is also an ortho para activator. So we're going to go here, here, or here for the OH. And then for our other guy, we are going to go here. Oh, crap, I drew my arrow wrong. We're going to go here, here, or here. Remember, this guy here likely won't form because of sterics. And since we do not have any meta deactivators here, we are able to carry out with our Fritocrafts. So remember, this guy can undergo rearrangement. So if I took this guy like this, with a positive charge here, we will shift this positive charge over here. So we will end up with that. It's kind of hard to see, I'm sorry, but yeah. That is how we will bond it on. So we will bond this guy. If I draw this molecule wrong, please do not hate me. I'm really bad at visualizing molecules. So give me a second. I think this is one of our practice problems. I'm always bad at visualizing it when we have a shift because my brain doesn't do it well. Okay. So with the shift, we will bond here, here, here. Let me draw it like this. Maybe this will help. I don't really know how bad I drew that, but it looks pretty bad to me. But I believe that is how many carbons that will be the bond. I'm so sorry, guys. I can't draw for the life of me. And then the other place it'll bond is over here. Thanks, Rose. Sometimes I just need that extra push. All right, let me try drawing it a little better this way. Okay, that looks a little bit better. It's still not great. It kind of looks like an awkward turkey, but it's okay. Hopefully you guys can see it. If you can't, you know, I'm sorry. And then finally we have this guy here. Our NO2 is a meta deactivator. And then this guy here is going to be a ortho para activator. This here, I know we didn't write it in, but it's over AlCl3. So this is a Fritocraft acylation. And since we have a meta deactivator present, we will not carry out this reaction because of this guy. It does kind of look like those cookie bats from Despicable Me. I'm glad somebody could see something out of this drawing. I want to pull up a picture of that now. Okay, I'm not going to get sidetracked, but we will later. Thank you. All right, guys, go ahead and take a screenshot of this. That basically wraps up 15. We are running a little bit behind schedule, but when do we not? So, any questions on this before I hand it back over to Rosemary so we can finish up chapter 16? I'm sorry that I stutter a lot and I always erase my work. And I'm sorry this kind of looks like a mess, but
Wait, could you scroll down a little bit?
yeah.
Thanks.
You're welcome. All right. And if you guys do have questions, just drop them in the chat and I'll answer them. But I will. Oh, thank you. A for effort.
Wait,
how's the last one? No reaction?
Yeah, if there's an activator.
So remember, it doesn't matter if we have an activator present. If we have a meta deactivator anywhere on the ring, we can't do the reaction if it's a Fritocrafts. So it doesn't matter if we have an activator or not. As soon as you see that meta deactivator, just know no reaction. Fritocrafts was always a weird one. Okay. So if that is it, I will hand it back over to Rosemary, and she will wrap up concepts for the night.
Hello. Okay. So let me share my screen. Suddenly I forgot how to exist as a human. Okay, there we go. All right. Just please let me know if you can see my screen. Okay, cool. So let's ignore that. Just casually planning a memorial. Anywho's. As I promised, we're going to go through this super quick, which is just the naming of different benzene rings with substituents. We're going to do the common name and the IUPAC name. We're going to do this super quick. So, if we have a benzene ring with a methyl on it, that will be called toluene. I'll zoom out a tiny bit. And the IUPAC name is methyl benzene. If we have an NH2 on the ring, we will have aniline. And the common name, the common name is aniline. And the IUPAC name is benzyl amine. Next up, we have the ester substituent. So the common name for the ester will be anisole. I think of aerosol, and that just makes sense to me. I don't know why. The most correct IUPAC name is methoxy benzene. And my students pointed out to me you guys are all my students, but in my SI session, that there are a couple different technically correct names, depending on what textbook you look at and what naming rules you follow. But I'm letting you guys know the most correct IUPAC name is methoxybenzene according to the IUPAC website. And someone said, I don't know why I don't have this page. Honestly, it's because I forgot to include it when I sent it to you guys. And then I added it just now. But I will send it to you again in the cheat sheet, like with these questions. So don't freak too much. But I do apologize for the inconvenience. So when we have an alcohol on our benzene ring, we are going to call that phenol. And the IUPAC name is going to be hydroxybenzene. Please note the hydroxybenzene because a lot of people forget that it's called that because it's also called benzyl alcohol. So please don't forget the name hydroxybenzene. That's the one Dr. West likes to call it on the exam, excuse me. So going down to these ones, remember I will zoom out at the end. But when we have an aldehyde present, super simple, we're going to call it benzaldehyde. And that's pretty much going to serve as the common and IUPAC name for us as far as we need to know. So when we have the ketone, we are going to call it acetophenone. And the reason it's acetophenone is because we have this acetone on the benzene. In IUPAC naming, we can also call it methylphenylbenzene. Sorry, methylphenyl ketone. And the only reason I give you that is because once in a blue moon, he'll name the ketone that way instead of acetone. And so I just want you guys to have seen it before. Usually we'll call it just acetophenone. And the last one is when we have a carboxylic acid, and we are just going to call it benzoic acid. And so I'll zoom out so you guys can take a look at that. And also, I don't know if you guys can tell, but I can definitely hear it. I know my voice is kind of shaky, and I know my hands are kind of shaking. So it's, just pretend it's not happening, please. I apologize if I, stutter or say anything wrong. I will correct myself. But yeah. So I'll give it a couple more seconds, and then we will move on to chapter 16. I'm going to try to go through it as fast as possible without losing you guys. So just let me know if at any point I go too fast or whatever. All right. And then someone asked a question about naming. So we're going to go into more naming questions. This is just the basic stuff we have to know. We will cover more naming stuff in a little bit. Someone said chapter 16 is scary. No! It's my favorite chapter. Hopefully it'll be less scary by the time we're done with it. Okay, so we're not going to do reaction mechanisms this time around because who needs that, right? I love reaction mechanisms because I'm a weirdo, and I personally think you guys should know them for yourself. Because it helps with the background concepts. However, you don't have to know it for the exam. You just need to know reagents and final products and a couple different key points out there. So that's how we're going to go through it today. I call that the rosemary method. All right. So the first reaction we have is the gem-diol reaction. And the gem-diol reaction is when you have a ketone or an aldehyde reacting with H2O and either acid or base, and you are creating this thing right here, which is called a gem-diol. The reason it's called a gem-diol is because it's two alcohols on the geminal position, aka on the same carbon. Please note that all of the reactions in this chapter are going to be at equilibrium, which means they will go back and forth. That's why I drew this arrow, the equilibrium arrows. All the other reactions, I got lazy and I just wrote the regular arrow. But just know that all of them in this chapter are going to be at equilibrium. If there's something important about the equilibrium, I will point it out to you. And someone asked, aldehydes would work too? Yes, they would. I just didn't draw them because I didn't want it to be like repetitive. Both will work. Again, all of these are also pretty much going to apply for ketones and aldehydes. That's why I only draw them one time. If there's ever a difference between ketones and aldehydes, I will let you guys know. I promise. All right. So the only thing I want you guys to note for the gem-diol reaction is that usually the ketone form is preferred. The gem-diol form is not usually preferred because it's less stable. If we react with base, though, as our catalyst, it will push equilibrium towards the gem-diol, and that will be slightly more preferred. In the case of an acid, though, it will push equilibrium more towards the ketone, so we will even more so prefer the ketone form. And that's pretty much all you need to know for gem-diol. So remember, ketone or aldehyde with H2O is going to make a gem-diol. If you have an acid catalyst, you prefer the ketone. If you have a base catalyst, you prefer the gem-diol. And that is it for the gem-diol reaction. Question?
Can you repeat that one more time?
Yes, I can. Okay. So summary for gem-diols is when you react a ketone or an aldehyde with H2O, you will form the gem-diol. If you use an acid catalyst, you prefer the ketone. If you use a base catalyst, you prefer the gem-diol.
So what this means is that, like, so if it has an acid, it'll stay as the reactant?
So all that is saying is that the equilibrium will push more to one side. So like this reaction will still happen, but we will prefer the ketone form because that will be more stable.
Okay, yeah, that makes sense.
Okay, cool. I wrote biol, I'm sorry. And yes, the same thing applies to aldehyde. Okay. So the acetal-ketol reaction is a little bit more complicated just because there are a couple different outcomes that we can have. So I'm going to try to say it slowly. So when we react an aldehyde with an alcohol and acid, we are going to make the hemiacetal intermediate, and then we are going to make the acetal final product in acid. If we had a base catalyst or we had no catalyst at all, we would stop here at the hemiacetal. We would not go to completion. So I'll say that one more time. If we have an acid catalyst, we will go all the way to completion and we will form the acetal. If we have a base catalyst, or if we have no catalyst, we are going to stop at the hemi and we will not go to completion. The same exact thing is true of a ketone, except you will form the hemiketol and then the ketol, and we're going to name those right now. So, when we have an R group and a hydrogen, we know that that is an aldehyde base. So it's either going to be an acetal or a hemiacetal. And since there are two OR groups, we know that that is an acetal. This second one has the same base, but it has one OH and one OR. So we know that is a hemiacetal. As I said, same exact thing is true of ketones. So when we have two R groups, we know that is a ketol base. When we have two OR groups, present, when we have two OR groups present, we know that we have a ketol. And when we have one OH and one OR, we know that we have a hemiketol. And I will repeat the rule I said before one more time. So in an acid catalyst, we will go to completion in both the aldehyde and ketone case. So if we have acid, we form the acetal and the ketol. If we have the base or no catalyst, we are going to form the hemiacetal or the hemiketol. And I know Katrina also said that in the chat. So if you need to hear it one more time, please refer to the chat. Any questions about this reaction? Okay, doesn't seem like it, so I'm going to move on, but let me know if you have any questions at any point. So the next one we are going to go over is the imine formation. And so the imine reaction is going to take place whenever we have a ketone or an aldehyde reacting with this kind of group. And this is just going to be a primary amine. So this CH3 can be replaced with any R group. So again, I will say ketone or aldehyde plus primary amine will give you your imine. So all we're going to do is cut off the oxygen and replace it with our amine. And this will happen in both acid and base. There won't really be a difference between our acid and base. Someone asked, is this like an E2 mechanism? Let's not really think of it as like E1, E2, or S1, S2, because it doesn't really work like that. That's the short answer. Okay, so the hydrazone formation is going to be kind of similar, but instead of an amine, we are going to use something called a hydrazine, which is two NH2 groups stuck together. So all we're going to do is take this oxygen and replace it with the nitrogen, and it will have an NH2. And I just realized that I didn't give you a catalyst. I'm not sure why I did that. That was an accident. I'm writing HCl just for consistency, but this will happen in acid and base equally. And someone asked, is that a secondary amine? So no, not exactly. It's its own thing. It's not an amine at all. We're going to call it hydrazine because it's two NH2s attached to one another. And so our final product is going to be the hydrazone. It's very important that you guys know which one is the hydrazine and which one is the hydrazone. And the way I remember that is hydrazine, you go into the reaction. Hydrazone has that O, and there's two ways to remember it. You can either think of it as in and out. So you put this into the reaction, you get this out of the reaction. Or you can be weird like me and think hydrazine, it goes in, hydrazone, oh snap, we're done with the reaction. That's the final product. I like to think about it that way because it's funny to me. All right, so this we didn't actually cover an SI, so it is kind of new. But we actually can have a case of the hydrazone reaction with excess. So if he gives you excess here underneath the ketone, we're actually going to get a different final product. And before I go into that, I just want to make sure you guys know something. So please listen. Okay, this might sound silly, but it's happened too many times. Excess can either be written out like this, or he can just say XS. These mean the same thing. And in the stress of the exam, sometimes people get freaked out, and I've had people be like, Rosemary, what does extra small mean? So I'm letting you guys know, it's not extra small, it just means excess. All right, so now that we got that out of the way, if we have a ketone in excess, we're going to do the reaction once, and we are going to get our hydrazone. But then we're going to have that happen once more, and we are going to add another ketone base up here. It's really weird looking, and we won't have to name it, but just know that this is a thing. Sometimes he asks it, sometimes he doesn't. People are freaking out in the chat, and I don't know what happened. I missed it, but it's okay.
Jared said, instead of excess, he can say, or he can say, the love I have for New Zealand.
Damn. Gotta love Jared. Okay. So, yeah, I know I went through this one really quick. People like to get confused or think too much into it. You don't have to know what this is named. Just know that if we have excess, we go through this reaction one more time. And so we're going to have two ketone bases bonded to both nitrogens. All right. The next reaction is the oxime formation. And sorry, someone said, can I go over it one more time? So let me do the oxime one, and then I'll go back, just because I already started. So the oxime formation, we haven't done this one in SI yet, so I'm going to go a tad bit slower. So the oxime will be formed when we have this right here. And this reagent is going to be called the hydroxylamine. And that's because we have a hydroxyl group attached to an amine. And in this case, we have to choose between nitrogen and oxygen being the nucleophile. And as we've covered before, we know that nitrogen is more likely to donate its electrons, and it's a better base. And for the same reason, it's also going to be a better nucleophile. So whenever we're given the hydroxylamine, we know that the nitrogen will act like the nucleophile, not the oxygen. So we're going to cut off this oxygen, throw it away, and we're going to replace it with NOH. Like so. And this final product will be called the oxime. So again, all you have to know, ketone plus hydroxylamine equals oxime. And this can happen in either acid or base, doesn't matter. Any questions? I know people wanted me to go back up to the previous one. And yes, whenever I finish, I will zoom out so you guys can see all of it. All right, so the hydrazone with excess, again, it's pretty much exactly the same as the regular hydrazone reaction. So we're going to get this here. And then we're just going to do the reaction one more time if we have excess. And we will end up replacing this H2 with the ketone base. So it's almost like a double hydrazone. And no, you don't have to name this. As Jared said, people still just call this the hydrazone. It has another name, but you guys don't have to worry about it. Someone also asked, can the oxime be done the same way the hydrazone was with excess? I believe that's what you're asking. So we're not going to do this in excess. The only one we're going to do in excess is the hydrazone. The other way I could interpret that is, could either of these be done with an aldehyde? In that case, yes, they could. So all of these reactions that we just did, the hydrazone with excess, and the oxime, can all also be done with aldehyde. and they can also happen with a base catalyst. You're very welcome. Okay. So the next one we are going to cover is the phenylhydrazone, which is pretty much exactly the same as the regular hydrazone. Instead, we are starting with a phenylhydrazine, and we have this little phenyl group attached, and we end up with our product being the phenylhydrazone, and again, we just have this little benzene ring attached. Again, this can happen with an aldehyde, and it can also happen in base. The only thing I want to add that's important for you guys to know, remember that only this nitrogen will react. We will not react with this middle nitrogen because it's much too sterically hindered. So we're only going to add on this end. So again, pretty much exactly the same. Aldehyde or ketone plus phenylhydrazine is going to give you phenylhydrazone. The next one is the the enamine reaction. And the enamine reaction is almost the same setup as the imine reaction, so I want you guys to be careful. The only difference between the imine and the enamine is that we are using a secondary amine instead of a primary amine. That's the only difference in the reagent. The reason I gave you pyridine, and I have such trouble pronouncing that, so I'm sorry, is that on the exam, Dr. West just usually gives you pyridine. It's just a base. I just wanted to include it just in case you see it. Don't freak out. It's just another base. This could also work in acid, but it's better if we use base. All right. So in the reaction, this is going to be slightly different than all the other ones because now we are too sterically hindered to get this same kind of double bond. So instead, we're going to perform an elimination reaction, and we're going to form a double bond to one of our alpha carbons, and we get our enamine. I know I gave a lot of vocab words, and I'm going to go through and explain that one more time. So please remember that the alpha carbon is the one right next to, or just to be more correct, I'll draw it here. So the alpha carbon is the one next to or adjacent to the carbonyl carbon. And in the case of the enamine formation, when you have a secondary amine, you will have to take one of these alpha hydrogens, form an elimination in order to get the enamine. And so one thing you need to keep in mind is what would happen if we didn't have a symmetrical ketone. So if we had something like this, let's say, right? Now we have two alpha carbons. And in the case of something like this, where they're not symmetrical, you are going to take a hydrogen from the most substituted side. So in this case, this would be the most substituted side. And the reason for that is it will make the more stable double bond. Versus, I'm going to draw it smaller to symbolize that it's not as favorable. That. So this is the less favorable double bond. This is the more favorable double bond. And just to reiterate, we are going to take a hydrogen from the more substituted alpha carbon in order to get the best double bond as our final product. And so then that also raises the question, what happens if the ketone is fully substituted on both sides, such as in this case? So the ketone has no hydrogens available on this side and no hydrogens available on this side. So as someone said in the chat, that would have to be no reaction. Because we don't have a hydrogen, we cannot do the reaction. The same thing goes for aldehydes. I know I keep zooming in and out. I'm sorry. But if we have a regular aldehyde, we are already kind of at a disadvantage because we only have one alpha carbon. So we have to be very careful. You're never going to take this hydrogen away because it's not on an alpha carbon. And if the one alpha carbon on the aldehyde ends up being fully substituted, you will not have a reaction. So this one can react, this one cannot, because the alpha position is fully substituted. So let me zoom out so you guys can see the whole thing. The enamine one is pretty complicated compared to all the other ones. So please let me know if you guys have any questions. I'll give you guys like 30 seconds for this one, and then I'll zoom out so you guys can see all of them.
Oh, could you repeat why it was reaction? My bad.
Yeah, no worries. So the reason it's no reaction here is because both of the alpha carbons, which I will just write down here. So both alpha carbons are fully substituted, meaning that they have no hydrogens. And so if there are no hydrogens on the alpha carbons, we cannot do this reaction because we would not be able to do the elimination. So we are required to have an alpha hydrogen in order to do the elimination and get our final product. If we have an asymmetrical ketone, meaning we have two different R groups, the side that has a more substituted alpha carbon will be preferable because it makes the better double bond. And that's much better than this one. If we have an aldehyde reacting, we're never going to take this hydrogen that's coming off of the carbonyl. We're only going to take a hydrogen from the alpha carbon. So this will work. This hydrogen will react. But if our one alpha carbon is fully substituted, we are not going to be able to do the reaction because, again, just like in this case with the ketone, we have no alpha hydrogens, therefore we cannot have our reaction because we cannot do an elimination. And then Jason asked a really great question, which was, will this example lead to a major and a minor product, or will this one just not exist? We will technically have a major and a minor product. This will be the major product, and this will be the minor product. And theoretically, Dr. West could ask about either one, but typically he's only going to ask for the major product. If he wanted the other one, he would have to specifically say the minor product. If he doesn't say anything about major or minor, just stick to this one, if that makes sense. Okay.
Okay, so for the first example with the aldehyde, we are gonna go ahead and substitute it where the alpha carbon is, right? Because that's the only one that there is.
Exactly. So I can even just show you the final product really quick, just so you guys have a reference, I guess. So it would look like that. Okay, so now I'm going to Sorry. Oh my god, that scared me so bad. So I'm going to go to this page first and let you guys take a screenshot of this. And then I will zoom out and let you guys take a picture of the second page. Or scroll, not zoom. I don't know what I'm saying anymore. I'll give it until I take a sip from my water, and then we'll scroll down. Okay. Ta-da. And for the cyanohydrin one, I'm really just not even going to cover it. Just know what it looks like. This one never shows up on exams. And according to the email that Dr. West sent us, we don't believe it's going to be on your exam. I included it here just in case so that you've seen it at least one time. But I'm not going to waste time covering it because it's probably not going to show up. And then Katrina also already answered this in the chat, but a couple people were asking, so I just want to say it out loud while you guys screenshot. So there will not be SI or tutoring tomorrow because it is a holiday, so campus is technically closed, which means we can't hold our usual sessions. Okay, any questions before I move on? Tomorrow is better
So,
I think. Yes, what's up?
no matter how substituted the cyanohydrin is, when it reacts with that H2SO4 and H2O, would it still have that pattern?
So if both sides are fully substituted, it would be no reaction. But other than that, if you have at least one alpha hydrogen available, that will be the product.
Okay, thank you.
That's a really great question, though. You're welcome. Okay, so the last one, and someone said that this was like the really hard part of chapter 16, but trust me, Rosemary's got you. Okay, so, sorry, I got too excited that I lost my train of thought. All right. So for the Wittig reaction, we have the real way to do it, and then we have the Rosemary method. So I have to show you the real method because that's part of my job, but then I'm going to show you the Rosemary method, and hopefully everything will make a lot more sense. So stick with me, please. All right, now that I said all that, let's actually get into it. So first of all, we have this thing right here, which is just called an alkyl halide. We've covered that a couple times in the past, but naming is kind of a weird thing, so I'm going to include it for you guys again. I don't know what I just said, so let's not even talk about that. Okay. So now we have something new called PPH3, or triphenyl phosphate. Triphenyl phosphate, or PPH3. So when we have PPH3, it's essentially going to come in and replace this right here, the halogen. So we end up with this right here. And we get a plus on the phosphorus. So now at this point, we also have this hydrogen here. And so in the second step, we are going to react with this bad boy, C6H5Li, and I'm going to draw that out for you. It's just a benzene ring. with a minus charge. And so all it is a very strong base. That's all it is. So that's going to come in and steal the hydrogen and form a double bond. And let me zoom out real quick. That would mean our final product is... Sorry about Bear. He's freaking out about nothing. So once we steal that hydrogen, we are going to have this guy, but the more stable resonance structure of that is going to be no, stop it. What am I doing with my life? Okay, so sorry about that. I just wanted to fix it. So, the long-winded reaction is what I just told you. In summary, just know alkyl halide plus PPH3 and C6H5Li will give you the ylide, which is this thing. Know that both of these are the ylide. They're both resonance structures of it, but this is the more stable one. So if he asked you which of the following is the ylide, both of these are correct. If he asked you which of the following is the most stable resonance structure of the ylide, this is the answer. And I will say that one more time because he does ask about that usually. So, if he asks you which of the following... Yeah, what's up?
Will he ask us any specifics on the reaction mechanism itself, or do we just need to know the product and which one is stable? The most stable version.
So there is I will show you an example that's like the hardest example he'll show you guys, where it kind of seems like you need to know the mechanism. But if you just know this reagent plus this reagent gives you this final product, you're good.
Thank you so much, Rosemary.
You're very welcome. And so this is pretty much step one of the Wittig reaction, because we created the ylide, and the ylide is going to be the reagent in the Wittig reaction. So we haven't done the Wittig reaction yet. We've just prepared the reagent. And so the actual reaction mechanism is going to be between any ketone or aldehyde. And I'm just going to write R1 and R2 plus the ylide, which, as we made before, looks something like this. And I'm just going to write R3 and R4. Because it can be any R group. I just want you guys to have like a stable number on it, just so you know what is what. Okay, so in the actual mechanism, I'm just going to show it to you one time because we haven't done it in SI. You're going to make this really ugly looking box. And so we have our oxygen up here, and it's bonded to R1 and R2, right? And that is going to react with phosphorus. And phosphorus is attached to 3 phenols. We already know that. But it's also attached to R3 and R4. And that is then going to react with this carbon. So we call it the box mechanism because it forms a box-looking thing. And at this point, I'm going to zoom in. And we are going to have this break. So that bond is going to break and give electrons to the oxygen. And then the electrons from oxygen are going to go here to form a double bond. So this bond will break and give the electrons to that carbon. And so the carbon will then form a double bond. I know that's really ugly looking. And again, I'm just showing it to you so you guys have seen it at least once. But this is going to create two products, one of which will be oxygen double bonded to triphenyl phosphate, which looks like so. And that's kind of like the side product because we don't care about it. That's formed every single time. The product we do care about is the one that has our R groups. So R1, 2, 3, and 4 are all attached to one another by a double bond. And I'm actually going to just move this over here to the side, just so everything is less squished. So I'm going to zoom out to show that to you guys. I know it's ugly. Please don't freak out. Just know that this is the full box mechanism that Dr. West covers in lecture. And I'm sure other people were also wondering this. I just saw this in the chat. So R3 and R4 are just whatever R groups or alkyl groups are going to be on the ylid. It can be anything. Same is true for R1 and R2. Those are whatever R groups are part of the ketone. So now it's time for the rosemary method. And I need you guys to pay attention, and then you will never forget it. Trust me. Okay. So we still have our handy dandy ketone, right? And we have our handy dandy ylid. And so all we're going to do is we're going to cut off their heads. So executioner style, we're just going to chop off their heads, throw them in a bucket. We don't need it. Bye-bye. We don't care. Garbage. Now we're going to be Dr. Frankenstein, right? And we're going to be complete weirdos. We're going to take the arms of our ketone and we're going to attach it to the legs of our ylid. So we're throwing away the heads. Remember, those are garbage. Throw them away. And so now we take the arms and legs and attach them together. Before I draw it out, usually this works better in person, but whatever. Hopefully you guys can still see me, right? Okay. So my head is gone. Whatevs. We don't care about it. My arms are R1 and R2. My legs are R3 and R4, right? I can flip around my arms because I can either go this way or I can go this way. Same with my legs. I can either face this way or I can face this way, right? But I can't exchange an arm for a leg. So I can't swap R2 with R4 because it doesn't work that way, right? But I can flip around R1 and R2 because those are my two hands. We can just flip them, right? And so with that logic, I don't even know if you guys could see me. But whatever. So R1 and R2 are the arms. And they are going to be attached to the legs, which are R3 and R4. Ta-da! Oh my god, someone said they did that with lizards? I'm not gonna judge you, but that's pretty fucked up. Anyways, I hope you guys liked the rosemary method. We're going to do it one more time with an actual example, and we're going to substitute the R groups, just so you guys can see better. So let's just say we have this for our ketone, and we react it with something like that for our illid. Okay, and I'm just gonna move it down a little bit, just so I have space. So again, we're gonna cut off our heads, throw it away, we don't need it. Cut off the head, throw it away, we don't need it, right? And so now we're gonna attach the arms and legs. So we can either attach it this way and do this, or we could have some flip-flop going around or happening. I don't even know what I'm saying anymore. So we could flip it around and it could look like this. What in the world? Right? So we flip those two around and we could keep this the same. Or we could have flipped it the other way. There's like a couple different ways we could rearrange this and make it work, but I'm just showing you guys two of the examples. So both of these are equally correct. What's not going to ever be correct is something like, why did I do it backwards? The world may never know. You can never do this. And the reason we can never do this is because you can't mix your arms and legs. You can flop around the arms, you can flop around the legs, you cannot swap arms and legs. And that, my friends, is the rosemary method. So let me zoom out so you guys can see this whole page. I'm sure that was a lot to take in. I had to stop reading the chat because it was making me laugh. What is the product's name? That's a great question. It's just an alkene. So the name is going to differ for every product, but in general, we can say that ketone plus illid equals alkene. And I'll actually write that. Ketone plus illid equals alkene. Alrighty. So I'll give you guys like 30 seconds or a minute just to... Okay, at this point we're done with concepts. But we're not done because I promised you guys we would go over some practice problems. So we have a set of practice problems ready. We are probably going to run over time because when do we not? But yeah, you're free to leave at any point. I'm not going to force you guys to stay because you can watch it again later. But we will stay over time and do the practice problems for you guys. But yes, so I'll give you guys a minute just to reset, refresh. I know 2.5 hours is a really long time to focus on Orgo. So take a minute, breathe, reset, get a drink of water, get a snack, and then we'll start with practice problems.
And guys, these practice problems are problems that you have not seen yet from the practice problems on Canvas. So just a little heads up, we are going to be going over problems similar to the ones on Canvas, but you will not find them on Canvas. So, yeah.
If you guys remember from my session that one time, it's the practice problems you have, but spicy. And if you guys were at my sessions, I mentioned one time that I was going to go through and... Sorry, you guys make me laugh. I was going to go through and pick out like the really good ones that you guys should focus on. That is what we are going to show you guys now. We decided not to send out this set, though, just because we decided it's best for everyone, because we have not seen your exam, and we felt that if we sent you guys, like, a set of practice problems, people might think that, like, you should only work on those, or that that's going to be exactly what the exam is like, and it's not the case, so we don't want to advertise it that way. But, wink, wink, we will be doing the problems, and I will let you guys screenshot before and after, so you guys can still have them. Someone is unmuted. Did you have a question?
Yes. For these reactions, I wanted to ask when the stereoisomers occur, because I'm asking because I saw these two questions. It's on the practice problems. I mean, I kind of memorized it because I don't know how it got to that answer, but I don't. If you were to ask it in a different way, I wouldn't know how to determine that.
Yeah, that's totally valid. I decided to include those questions, actually, and then just wait to talk about stereoisomers until we're doing those questions, only because I figured it would be easier to see it in that format. So yeah, I will cover that, though. That's a great point. And yes, those questions will be included in the YouTube video. But I'm actually just going to stop